ما بالهيلة عايش что сообщили сегодня. А значит, была лекция по дифференциальным уравнениям. Я еще раз читал, там, где дружался лекцию про уравнение теплопроводности. Значит, вдруг среди лекции открывается и лекцию отпихивает. Говорит, пожалуйста, все говорит неправильно. А надо говорить вот так. То есть, я сказал, если вообще нет лекции для студентов, значит, туда врывается Сашенко и говорит, что это я не говорю, что ну, конкретно первую снял статью, рецензировал Саша Молодцова. Значит, мой потом сильно просто. Ты что? Рецензия была так. Статья очень хорошая, но главную теорему доказываете неправильно. Главную теорему нужно доказывать вот...
Хорошая, написать ее надо.
Вот так вот. Он предложил другое доказательство. Ну, более-менее он сказал, что надо переписать всю статью, чтобы доказать, как, в общем, он хотел. Не знаю. В конечном счете, она опубликовалась. Да. Окей. Yes. Cusp view. Yes. In principle, you have a cubic that's a Russian notation. Yes, of course, I'll state it. Yes. There's certain ways. There is all French with description by the same people who did a version online. I have a description with a picture. We have in terms of universal for function. So can you consider C2 with cusp singularity? This is a version with this particular my question from this one. What would this even be? Because it's not smooth. Yeah. So that. Share experience about this. I mean, what's inside? What would be the variety of the it cannot be a cusp because it's homogeneous. You can imagine what happens. Yes, I think there will be something related to yes, what so important. Sometimes I want to down on to get in too much complicated now. I should really tap on board. Since this you mentioned the Rina Anno involved with K1. Yes. That is only generic component. Yes. And I was need necessarily to understand more details. And in particular, parking yes. Even generic component seen. Okay. And these data I need to control you can discuss it.
So this morning is by Rina Anno, and she will tell us about Barr-Beck theorem for enhanced triangulated algorithms. Let's start.
Right. I would like to start with thanking the organizers for inviting me here. It's a great pleasure to be at this conference. And this is work with Philology and Sergei Arshich. So first, let's start with the title of the talk. What is Barr-Beck's theorem, also known as monadicity theorem? That's a theorem from history when you have a of adjoint functors between two categories A and B. So you have a functor F in its right adjoint R. Then RF is a monad. So we have multiplication operation from RF to RF. And one can define an Eilenberg-Moore category E, which category theorists call the category of algebras over this monad, which is unfortunate for an algebraist who is accustomed to call this an algebra and these modules. So so that these would be objects of A with an action of RF on them. So an object X with a map RFX to X. So algebras or vector of the modules over RF and Barr-Beck's so monadicity theorem answers the question when the category B is equivalent to this category E. In that case, the junction. In that case, the category B is called monadic. And one example of a monadic category will hopefully explain why this is relevant, especially in the algebra setting. If A is so if A says grade A is an algebra and grade B is an algebra over A. And now we have induction and restriction. Between mod A and mod B. And so then in that so this is a monadic example.
So B is an algebra containing A or something else, or B is an A algebra in some other sense.
There is an algebra morphism from A to B.
Oh, okay.
then we have induction and restriction. They are joined, and they so note that induction is then tensor tensor product with B. So over A, where B is viewed as an AB bimodule. And restriction is tensor product over B with this, so with B again, where B is viewed as a BA bimodule. So when you compose them, then the monad is then B viewed as an AA bimodule. So that's an algebra object in the category of AA bimodules. So in the monoidal category of AA bimodules. So we would like to extend this theorem to triangulated categories. The problem is that the original categorical construction, so when we define an algebra over a monad as an object with action of the monad, does not carry any triangulated structure. So if you're even if you if your original, so if your categories are triangulated and your factor is exact, you still can not put a triangulated structure on the category of RF algebras. So our solution to this problem is to consider enhanced triangulated categories. So triangulated categories that have DG enhancements. So the setting for my talk today is talking about enhancing triangulated categories by DG, and talking about, so most of the talk will be spent talking about some DG categories and some A infinity structures. So enhanced triangulated categories were introduced in the 90s by Professors Wondel and that so DG category A enhances a triangulated category T. If C is the homotopy category of a DG category.
Just about algebra. So what is this statement that it's monadic? And who is monadic, by the way? It's terminology.
The category not B.
Monadic
Or S. Yeah, so that category mod B is so mod B is equivalent to mod modules of this monad.
which is modulus of this bimodule. B is an A bimodule.
Yes. So and this monad is a so B as an A bimodule. So because modules over B are vector spaces with the action of B. Modules over this are A modules with additional action of B via tensor product over A. But if B acts on a module, so we are in purely algebraic situation, B acts on a module, then that's a map from tensor product of this module with B over K to this module, and it factors through tensor product over A, because A has an algebra morphism to B.
Mark off, I mean, when there is a question: when is the category B equivalent to the category of modules in A over the monad? And that's when F is called monadic, basically.
B is equal to B.
Yeah.
It's is equivalent to this category. This is currently B, this example. And this is the algebra 4 category, categories of algebras over this monad. Yet in this example, currently B is equivalent to the algebra 4 category. Because if something is a B module, it is also an A module through a map from A to B. So through the algebra morphism from A to B. So the action of B incorporates the action of A. So the tensor product over K factors through tensor product over A.
In the modular context of upper board, there is always a natural comparison functors. So there's a functor from B to E. The question is, when is this natural functor? And
It's just question that you don't need A to be embedded in this.
That's taken care of because the objects of these are not modules, all modules over A. They are modules over A with the action of induction restriction function. So, for example, if induction restriction takes a module to 0, then there is already 0 action. So, yes, so consider Rita enhancements where triangulated category T, so where we say that DG category A enhances the triangulated category T, if T is the common derived category. Then why? So this is highly applicable to geometry because after the pioneering work of Wonderland Vandenberg in 03, then worked on and expanded by several people, including Ruhia, Taboada, and Bloons. Derived category of sheaves on a wide class of schemes are equivalent to derived categories of modules over DG algebras. So studying enhanced triangulated categories in a sense. So studying derived categories of modules over DG categories and factors between them. It's not it's not only a representation theory thing. It is also helps get results in algebraic geometry. So, so that's the setting. So how do we how can we possibly define the Eilenberg-Moore category for enhanced functors between enhanced triangulated categories? So first of all, so by Toyn defines a homotopy category of DG categories. Yeah, it says that enhanced triangulated functors between derived categories of modules are in one-to-one correspondence, so are equivalent to the derived category of bimodules over 2-digit structures. So we can think of functors between enhanced triangulated categories as objects in this derived category. However, this derived category is triangulated. We don't like working between triangulated categories, so working with triangulated categories. We would like to enhance this category as well. So, however, this proved to be somewhat challenging. So, how do we? So, can we possibly define a bicategory where objects are small dg categories and morphism and morphisms form dg categories. So one morphisms enhance this.
This is something called the DG by category. By category whose one morphism category is a DG category.
The thing is that so this is something that people immediately wanted after seeing Cohen's result, but it proved to be not a thing. There was a paper by Demarkin in 2007 that is called "What do DG categories form?" ? So it is. So apparently one cannot construct such a bicategory. So, however, we propose a construction of not quite a DG bicategory, but something that is almost a DG bicategory. And I will describe it in a moment. So that's maybe the answer to the market's question. However, this structure does not have a name. So maybe one should axiomatize it at some point, but it seems to be close enough to a bicategory for all practical purposes.
1.5.
So if I can add a small remark, after one of the conferences in Florida, Kontsevich sort of told me that any attempt doing that will lead to either associativity not being strict or unitality not being strict. So it's possible to.
It's exactly what we did, because what we define so what we define is a not exactly but something with objects. Small DG categories, and then one morphisms. So one morphisms from A to B, forming a DG category. However, the horizontal product, so composition of, so one morphisms form a actual DG category, but horizontal composition, so composition of one morphisms is associative, but only homotopy unital. And even then, so composition of one morphisms so we have phi from AB and psi from DBC, psi composition plus. Now there is a unit, unit dA from A to A, except it's not a unit, it's a homotopy unit. that you have unitary morphisms from so phi to phi composition, so phi A to phi, but they are not isomorphs. So phi composition IDA is also a one morphism from A to B. These are not isomorphisms. However, this composition is identity, and this composition, so they're not isomorphous, but they are, so they have they are semi-inverse to each other. So phi composition IDA phi to phi composition IDA again is monotonicity.
So if we can add a small remark, in a DG by category, you would have an isomorphism between phi and phi circ IDA.
I mean, in a by category, this should be a unit for horizontal composition, like
Unit up to isomorphism. And a homotopy unital is just saying that this is a homotopy equivalence. But we are in a better situation. We have homotopy equivalence with canonical inverse, which is real inverse on one side and inverse up to homotopy only on the other side. So this is sort of as close as you possibly get to really being unital.
and your position for so A and B are small DG categories. Our proposition for one morphism between small DG categories is essentially A infinity AB bimodules. Except just for technical reasons, we would so it's easier to work with DG bimodules than with A infinity bimodules. So A infinity AB bimodules. The thing is that A and B are DG categories, but we can view them as A infinity categories with zero higher operations, so just strict infinity categories. And then we can talk about A infinity modules and bimodules over there. This is equivalent to the category. So since A and B are strictly unital, these so every homotopy unital. So we always want our modules and bimodules to be homotopy unital, because for a strictly unital A and B, that makes them H unital. So that makes them have a DG resolution. So it is enough to take DG AB bimodules. With A infinity morphisms between them. So objects of this category are DG AB bimodules, and morphisms in this category is A infinity. And for computational reasons, we prefer the incarnation of this category, what we call the Barr category of modules. So Barr category of modules was introduced by Timothy and I. And it's a category whose objects. So it's a category whose objects are, say, if we are talking about category of bimodules, their objects are A, B, B, G bimodules. And the morphisms from, say, bimodule M to bimodule N are morphisms of AB bimodules from A bar tensor M tensor B bar N. So what's so A bar is a so bar
Nice.
so convolution of the complex where this is identity.
There is more to that complex.
Well,
Yeah.
identity tensor multiplication minus multiplication tensor identity, then here would be identity squared times multiplication minus identity multiplication identity plus multiplication tensor identity squared, and so on. So that's bar complex of an algebra A with multiplication M. Is this complex? In particular, so one point of this is that this is a free resolution by A, so by free AA bimodules of the diagonal bimodule A. So if you map this to A by multiplication, you get an acyclic complex if A is the unit of. So if you tensor this with a module and take just the usual DG module morphisms from this to another bimodule, this models the A infinity morphisms from this to this. Because what's the data of an A infinity module, A infinity morphism? It's a bunch of maps from M tensor a power of A on the left and the tensor power of B on the right to N. This is exactly what we have here, and they, yeah.
This is the correspondence between the infinity modules and free DG comodules.
Right. So this, and then when we want to compose this morphisms, we start with we start with, so say if we have a map from M to N or from N to K, and each of them is an element in this thing, then if we just apply a map from M to N to this, we get simply N, and then we can't apply the map from N to K because it requires two bars on the side. However, this complex is a co-algebra. So co-associative co-algebra. That just takes a tensor and cuts it in two in almost fluids. No sense. Just everything in. So we can co-multiply this and this. So go to A infinity So A bar, tensor M, tensor B bar, tensor B bar. And then we can apply first map to the inside and get into A tensor N tensor B bar. And then apply the second map and get to B. So if you want to compose several maps, you need to split your bars and use the inside bars to do the map. Again, this is exactly what happens when you compose A infinity maps. So this is not any new evolutionary concept. This is just a way to visualize A infinity morphisms if you want. So these are the categories we use to enhance the morphisms between two right categories. The thing is that the unit object in this category is the diagonal bimodule. However, a module or a bimodule, right, and then the tensor, so the monoidal operation in this category is M tensor B bar tensor F. So you insert a bar complex in the middle. So so diagonal bimodule. So if you have A of A bar times
Sorry,
M
and the standard product is over what? Quadratic.
over B. Over B, yeah. Thank you. That's actually important. So M is an AB bimodule. We multiply it over B with bar construction, multiply it over B here again. So this is a complex. In the right, note that the rightmost term of this complex is tensor product over K, because the bar construction and these are all tensor products over the base. So this is essentially a bar tensor A M, which is homotopy equivalent to M, but not isomorphic to it. So, and that's the source of the problem we have here, that the horizontal composition is only homotopy unital. However,
So for ID tensor.
yeah, also, so on both sides. So this is same thing, completely symmetric. If we, so however, this coalgebra structure is, so it's not unital, but if you split a bar into two and then collapse one bar, so how do you collapse a bar? You can take this complex and just map it to A by this map. This is a so this is a quasi-isomorphism. In the so, and the good thing about the bar category is that it is essentially the category of infinity modules. In particular, quasi-isomorphic objects are homotopy equivalent. So that contraction of the bar complex into a single A is homotopy equivalence in the bar category. And if you split a bar complex in two and then collapse one half, that's actually identity. So this composition is identity. However, this composition is not. So this is so this was all very technical. What do we do with it? So the next segment of the talk is also very technical. So DG categories. Turns out that this not quite by category structure is, however, enough for our next goal is so we want to define okay, that was something that I have erased. Define the category of algebras, or define the category. I just want to call them modules. Define the category of modules over a functor. So if we have a functor in this bicategory, so one morphism in this bicategory from A to A, let's define the category of modules over it.
An algebra structure.
Yeah. So you need an algebra structure. However, so one obstacle here is that if you have a pair of adjoint functors, then RF has an algebra structure. Then associated graph from. However, when you enhance adjointers, you only get a homotopy adjunction. And so even then, so one would expect RF to RF, so the middle FR collapse to identity still be associative because we have several separated groups. So that's the order in which they collapse matter. But it turns out that in this any three version of this equivalent setting, apparently it does. So the homotopy adjunction, so the enhancement of an adjunction, which is a homotopy adjunction, doesn't form an algebra. Multiplication is not associative. However, it forms an infinity algebra. But in what sense? Because it's a factor. I mean, it's an object subset. A infinity is defined for vector spaces. But it turns out that it is quite natural to define A infinity structure on objects over any monoidal categories or bicategories like this. So where we have that's a product. So algebras and modules don't have to be in the same monoidal category. For simplicity, I'm going to assume that they are. So the problem is M1. So typically, objects in monoidal DG categories don't have an internal differential. And even when they do, when it's the category of modules, sometimes internal differential and the monoidal product don't interact the way we would like them to. But it turns out that to define an infinity structure, we don't need an internal differential, but we need the structure of the DG category. So we need differential on morphisms only.
In a sense, the technology of how to sort of hide or describe reliance on the internal differential is precisely the twisted complex idea that you had of using twisted complex data to modify the differential.
We are going to take the and pack them into differentiating morphisms, because we always have something like M1 composition M2 tensor M2 minus M2 composition M1 tensor M2, so things like that. So A is an object in the monoidal DG category, define the bar construction. So, and then have an I of A by the I to A, I equal than 2. Define bar construction as a twisted complex. No, so it's going to be a twisted complex, so we are going to have more morphisms than just the differentials. So this is, so Mi are morphisms that point to A. And we derive the morphisms that, so between A to the I and A to the J from MIs by certain formulas, so with signs. So for example, this morphism is going to be identity tensor M2 minus M2 tensor identity. And this morphism here is going to be minus identity tensor M3 minus M3 tensor identity. So this all or so this all comes from this whole thing is from the corporate construction. So from the algebra. So and we say that these are the infinity structure on A if the Barr construction is at least complex. So if these all satisfy equations for twisted complex introduced by Professors Waddell and Kapronoff in their 90s paper. In other words, if if you take the direct sum of these and modify the differential by all these arrows, we get a differential again. This is that this is equivalent to A infinity equations.
I have a small remark here. Objects in the monoidal G category, objects do not have a differential. Let's use Yono then, and they will get a differential. Then this twisted complex condition is precisely becomes a normal sort of.
So depends on what monoidal structure you.
I'm talking about mod K. I'm talking about the classical sort of. I can.
If your monoidal G category is mod K, then you get the classical construction. But even after embedded in mod A, so objects in mod A get the internal differential, but this internal differential is not a morphism of A modules.
Yeah,
so it's
yeah.
like there are
Each mod K, this is the unit embedding thing. But for arbitrary monoidal category, unit embedding does not work for the reasons that Rina said. But this definition still does.
Then this definition we can define so infinity algebras and modules and prove prove a number of results for ordinary A infinity categories and modules that work in this sentence. So one thing is we need to redefine quasi-isomorphism.
So this is just ordinary infinity structure.
If A is a complex of vector spaces, then yes, this is the ordinary infinity structure in A. However, A can be an object of some other monoidal DG category, like A can be a functor, A can be a module, A can be whatever else. We just get rid of M1, packing it into differential homomorphisms. So one thing we need to redefine in this is the notion of quasi-isomorphism, because we are no longer in the world of complexes of vector spaces, so we don't know what cohomologies are. So we want to say that so amorphism. So morphism. So a morphism between two modules is a collection of morphism from morphism from E to F. Fi from A, that's an I minus one. For F, so is quasi-isomorphism if, so that's the definition. F1 is a homotopy equivalence in the underlying monoidal DG category. So in particular, if our underlying category is graded vector spaces, then well, complex of vector spaces, then being a homotopy equivalence is the same as being a quasi-isomorphism. And so homotopy lemma means like quasi isomorphism, same as homotopy equivalence. And we have transfer of structure. We have free forgettable adjunction. So a bunch. So for some, so we also have various notions of unitality. So various degrees of unitality that I'm not going to describe it because I'm running out of time. So needed for some of this. We also have module-comodule correspondence under some conditions on unitality. And the big thing that we need for the present subject is that if so M and R enhance and say left, so if factor so LFR enhance and adjoint triple, then RF has the structure of an infinity algebra, sufficiently unital infinity algebra, and LF has a sufficiently unital infinity coalgebra. And the derived categories, so like the derived categories of homotopy unital modules and homotopy unital comodules. For these are equivalent. And I know that derived categories of DG coalgebras is a very touchy subject, but we propose to put H unitality. So have a cobar, dependent that cobar complex is acyclic as the cornerstone. So under sufficient unitality of the coalgebra and sufficient unit, so and homotopy co-unitality for comodules, we can. So our then we can say that the derived category is simply the triangulated hull of three. So everything is written down in terms of free resolutions and so and the equivalence. And it's also, and then the other thing is that if we have, so the other big thing about this is that if A and B are so having, so if A and B are both infinity algebras and they have algebra morphism, so infinity algebra morphism.
Or any monadal categories,
Yes, you can define this over any monoidal DG category. If you have a quasi, so an A infinity algebra morphism between A and B, and it is a quasi isomorphism, then there is a equivalence between the right. Then this allows us to define the Allenberg-Moore category in this setting, because we enhance our monad by an A infinity algebra object in morphisms from A to A in our almost by category. And then we take the derived category, so we take the derived category of homotopy unital A infinity modules over this as the Allenberg-Moore category. However, this is kind of a horrible definition, because who wants to prove anything about category of A infinity modules over something that's an A infinity algebra object in some category of whatever. So, however, we can see, however, this infinity algebra, so we can find explicitly a DG algebra, like an actual honest DG algebra, that this A infinity algebra object is quasi-isomorphic too, as an A infinity algebra object in A mod bar A. So let us have a two two so let us have to enhance the G category. So this is modules over some G category, this is modules over G category. Let's take an enhanced functor between them. Then this is a functor of tensor multiplication over A by some AB by module M. Then its right adjoint is equivalent to tensor multiplication over B by the right dual of them. So they're both tensor functors, and we have explicitly the bimodules that enhance them. Then home from M to M is, well, note that RF is then tensor product of M bar times the right dual, which is homotopy equivalent to home. So just home from M to M in the bar category. So home over D. So DG homes from M tensor B bar to M. This is a DG algebra because bar category is an honest category. So homes in it form an algebra. And this is equivalent to, so this is an A-infinity algebra. This is a DG algebra. So this is a representative in the class of quasi-isomorphism of infinity algebras, which is an actual DG algebra. So and have induction and restriction functors from this. And we also have a pair of adjoint, well, commodity adjoint, but so when you take H0, it all descends, so becomes triangulated and actual adjoint from here to here. Also given by very nice tensors. So for example, this, so this is tensoring over V by Barr. It be viewed as a V bar MM bimodule. Because this is a, so homes from M to B are a module, right? So right module over homes from M to M by composition. And this is tensoring with home bar BM. And this functor, so when you pass through to triangulated categories, this functor is actually fully faithful. So this is a fully faithful functor, and this is its right adjoint. So yeah, and then both, so triangles commute. So F factors through this, and R factors through this as well. And this is the, so in H0, this is the triangulated hull by the of the image of F. Now that would, so on the level of dB it would be very unusual to see that the image, so triangulated hull of the image of F, so fully faithful embedding with the right adjoint, so splits as a semi-orthogonal factor. However, this does not work for dB because this arrow takes you out of the compact category. So this only works for derived categories of quasi-B, so for the big categories of modules. So we have this. So this is essentially induction and restriction. So we can now break down every functor. So through a monadic one, with this being fully faithful. And yeah, I'm running out of time. Can I have 5 minutes? 5 minutes to talk about the set. Is that all right? Yeah. So application to geometric application finally of this is that suppose you have a projected variety X and you have Q to X, which is an open coupling. So it's the union of UI, union of UI, union of intersections. And these are all affine. So UI is spec for some Ri, Uij, spec of Rij. For some rings, Ri and Rij. And
Is I less than 3?
now all so this no over all ij. So this is a Cartesian square.
You have this Uij twice.
Yes. Yeah, and that's actually important because there are two projections. This and onto this. So the sum, direct sum of all Rij has two structures of direct sum of. So this ring has two structures of modules over this ring. You can restrict Ri to Rij and then multiply, or you can restrict Ri to Rji and then multiply. So you can use the first or the second index. Of course, they're intertwined by an automorphism of this. of this, but still there are two different actions. So we can view, so yeah, and like everyone knows, the composition of F upper shriek F lower star is isomorphic as exact factors to P2 lower star Q1 upper shriek, and same for upper star instead of upper shriek. So, and yes, I think that upper star, and this is an algebra, and this is a coalgebra. And this also have separate algebra and coalgebra structures. And one can prove that these isomorphisms are in fact isomorphisms of algebras or coalgebras.
Which category?
So that's a good question. So big categories, because we have this for big categories. In fact, so we have a version of this for compact subcategories, but it's just like the more involved. So derived categories of quasi-coherent, so unbounded derived categories of quasi-coherent sheaves. Right. This, so I don't want to go to the technical details of how to make it work for bounded derived categories. Yeah. So one is that here that so if you so here these are isomorphic, so these are equivalences. So the triangulated hull of the image of F is everything. So the category, so when we enhance this and apply the theorem, the category of modules, so when you consider the category of comodules, category of comodules over this, well, first, this, so this leads to an A infinity coalgebra object, and this also leads to an A infinity coalgebra object, and this leads to an A infinity coalgebra morphism. So this is not automatic, but so the one reason that we prefer to work with A infinity structures instead of say stable infinity categories is that we actually have all the morphisms and all the homotopes explicitly. So one can construct this infinity quasi-isomorphism. So the derived category of X is in fact equivalent to the derived category of comodules over this coalgebra. But this coalgebra has a very nice, this coalgebra, so in the equivalence, so in the quasi-isomorphism class of this coalgebra, there is, so this DG coalgebra object, infinity coalgebra objects in a weird category. There is a representative that is actually an true coalgebra in the category of vector spaces. This has a coalgebra structure. You map this to a direct sum of all Rikj, where Ikj are functions with a triple intersection. And then you split Rikj as a tensor product of Rik tensor Rkj over Rk. So this is a coalgebra in the category of bimodules over this. So yeah. Then you have a presentation of derived category of this as a derived category of comodules over a coalgebra in the category of bimodules over, again, something that's just an algebra. And is it, sorry for going over time and thank you for your attention.
Questions? No questions?
If not, let's thank the speaker again. We meet at 2.